Okay, welcome everybody. We're happy to have Peter Samuelson, who will tell us about Skein relations in representation theory.
Okay, thanks for the invitation, and thanks for coming. So this is gonna be sort of a survey style talk. So some things I say won't be 100% true. I have to plug in my. Right. So Skein relations originally came up in knot theory, and they're a way of sort of combinatorially describing invariants of knots. And then this was in the, about 1990 when this came up. And today I wanted to talk about some ways of interpreting these Skein relations using representation theory. So first I should tell you what they are. So a link is a knot, but with multiple components. So it's an embedded, some embedding of some copies of S1 into S3. And we consider this up to ambient isotopy. So I won't say precisely what that means, but basically you can move the knot around, but not, it can't cross itself. So that it needs to stay, it needs to be an embedding at all times. Roughly. Okay, so I'll be talking about the Homfley-PT Skein relation today. So this is, these are 8 different people, the initials of 8 different people, arranged in a way that's close to pronounceable. And it's because 8 people came up with the same thing at the same time, basically. So this is a linear relation between links, and it's defined locally. So if you have 3 links in S3 or R3, which outside of a ball are the same, and then inside of the ball, the 3 links look like this. So I've circled the ball inside of which the links are different. Then we can impose this linear relation between these 3 links. So here Q is a formal parameter. So this equality is living in the space of formal linear combinations of links. Okay. And it's called the Skein relation. And we also impose a relation that the unknot is equal to some constant. It doesn't really matter. Well, it matters what it is, but for the purposes of my talk, just think of it as some constant. Okay, so if you impose these relations, this term on the left-hand side lets you switch a crossing at the expense of sort of a lower order term. So it's not too hard to see that this relation allows you to unknot any knot or unlink any link. So we can turn any link into a linear combination of unlinks, and each of the unlinks is this constant. So these Skein relations allow us to reduce links to constants. Constants depending on the parameters Q and V. Okay, and this constant is the Homfley polynomial. And maybe I should write here. Let's see. Let's do it this way. So it's really a theorem that this is well defined, because to sort of reduce and link to this polynomial, you make a lot of choices. So let me write, I forgot to write this statement here, so maybe I'll write it now. So the theorem that was proved by these 8 people is that this is well defined. And it's not technically a polynomial, it's a rational function, but that's okay. That's just some technical thing. Okay. So, right, it's not at all obvious that this is well defined. It's actually kind of, it's not so easy to prove directly. Okay, so this is the sort of first way that these relations came up in this way that I'm describing. And I wanted to say one more thing about this, these Skein relations. So, so far, everything I've said, I was working in S3 or R3, but these relations make sense in any oriented three manifold. So this picture I've drawn looks like it's a projection of something onto the plane, but I can really think of this as an oriented ball inside of a three manifold. So if I have some oriented three manifold, I make just a formal definition of the Skein module. So that's vector space over the base field, I suppose. So you take formal linear combinations of links in this three manifold and you divide by the same Skein relations. So this is like a generalization of this Hamilton polynomial to other manifolds, but it's only defined in a formal way. So this vector space for other manifolds is usually big. Okay, so for S3, this vector space is one-dimensional. So I could actually write that here. This is another way to state this theorem. Is that the Skein module of S3 is just the base ring. So the content of this statement is really that the Skein module of S3 is not zero. Okay. So these vector spaces, if the manifold has some additional structure, these vector spaces also have additional structure. So for example, if the manifold has the form surface cross interval, then this vector space is actually an algebra. And the product is given by stacking in the 0-1 direction. Okay, it's sort of like it's a little bit like the composition in the fundamental group. And this stacking is associative because we're considering things up to isotopy, so you can rescale things in the 0-1 direction. Okay, so these algebras are very poorly understood, except in some small examples. So I wanted to give an example of a torus. This is sort of, I think before this, the only algebras that were understood for this Skein algebra were the annulus and the disk. So it turns out that for the torus, this algebra has a very nice description. So we gave an algebraic presentation of it. So it's generated by some elements p sub x, where x is an element in z squared. So you should think of z squared as the, I guess, the homology of the torus. So yeah, for every element in z squared, we pick a generator in some way. And then we show that these satisfy these relations, that the commutator of two generators is a constant times another generator. So if you commute p sub x and p sub y, then you get p sub x plus y. And the constant that shows up here is it's like this quantum integer, basically. So here D is the determinant of the matrix that you get, the matrix with columns x and y. Okay. So there's a lot of, this formula is simpler than you might expect if you just do some experimentation by hand. So there's a lot of canceling in this formula when x and y are not primitive. Maybe I should also say this, that there's an SL2Z action on the torus, and it acts in the natural way that you would guess on these generators. So it just permutes the generators. And you can see that it preserves this relation too. And it's also true that this is a presentation. So these are a sufficient list of relations. So I wanted to give one example of what this product looks like, because it'll sort of show up later maybe. So let me draw, I'll need a little more space. So I wanted to draw what this commutator means in one specific example. So if these vectors x and y are relatively prime, or sorry, not relatively prime, if x is primitive, then this generator is just a simple closed curve. Okay. So both of these vectors 1, 0, and 0, 1 are primitive, obviously. So this commutator is a product of two simple closed curves. And I'll draw what that is. So I can't draw the torus unless I draw a square. Actually, maybe I can draw it with two different colors. That's going to take too long. Well, I draw the torus in the standard way. So I'm identifying the edges of the square. Okay. So what's P1, 0? So this is a simple closed curve in the homology class 1, 0. So that's actually uniquely determined. And it looks like this. And now when I take this product, so there's two terms. When I take the product in the first order, the thing on the left goes on top. So I put this curve on top of the curve like this. That's the first term in the commutator. And the second term is the same, but the heights are flipped. So then I multiply P1, 0 as first, and then P0, oops, sorry. I said the wrong thing, but I drew the right thing. Okay, so that's the commutator. Now, I see a crossing here, and outside, away from this crossing, these two curves look the same. So I can, oh, green doesn't show up. It's green. Let's try this. Let's see, a red. Okay, so let me circle the, if I just look inside of this red circle, I see the Skein relation, the left-hand side of the Skein relation. Yeah, so if I rotate this square sort of, I guess, 45 degrees counterclockwise, then the red circles, inside the red circles looks exactly like this Skein relation. So if I apply this Skein relation, then I just get Q minus Q inverse times the resolution of this crossing, and there's a unique way. I just straighten out the curve, and it looks like this. Okay, so yeah, and right. So the thing on the right-hand side is a constant times P1, 1. This is a simple closed curve corresponding to that generator. So this this commutator relation in this special case is just exactly the Skein relation. Okay, so that's most of what I wanted to say about the Skein relations in, coming from topology. So now I wanted to give a couple ways that these show up in representation theory. So the first one is pretty well known, so I think I'll go through this quickly. The first one comes from quantum groups. So if G is a Lie group, then the tangent space of the identity is a Lie algebra. So we can, if you have a representation of the group, you get a representation of the Lie algebra, and that gives you a representation of the enveloping algebra of the Lie algebra. Okay, so I've written the definition here, but maybe I'd say more if there were more grad students, but right. So the group itself doesn't deform, but this enveloping algebra of the Lie algebra does have a nice deformation. And this has been very interesting in representation theory for quite some time. Roughly it's a deformation of this enveloping algebra where the relations depend on some formal parameter Q. And if you set Q equals to 1, then you basically get the enveloping algebra of the Lie algebra back. And a lot of the representations also deform. So for, say, for GLN acts on C to the n, obviously. And if you take tensor powers of this representation, which I'll just call V, the defining representation, then the symmetric group acts on V to the K. And this action commutes with the action of the enveloping algebra. So the symmetric group maps to, maybe I should say the group algebra. The symmetric group maps to the ring of endomorphisms of V to the tensor power K. Now what happens when you turn on this parameter Q to get the quantum group, this representation deforms. So I copy pasted this bullet point here and put in a couple of Qs. But I forgot to correct what I had written. So once you deform this representation, you no longer get the symmetric group acting on V to the tensor K. You get the Heck algebra. This is maybe hard to read. So this is an algebra which is a deformation of the group algebra of the symmetric group. And you can define this explicitly algebraically. So in the symmetric group, there's these relations that the square of the permutation is the identity. That deforms to a quadratic relation for generators sigma I, which are deformations of transpositions. So this quadratic relation, you can write it like this. You can write it as sigma I minus sigma I inverse is Q minus Q inverse. And if you represent these generators of the Heck algebra by the braids, by sort of drawings like this, so maybe I should make a remark. In these pictures, I'm really representing elements in the Heck algebra as, well, I'm representing the Heck algebra as the quotient of the braid group, the group algebra of the braid group. Okay, right. So the point is, if I think in this way, then I can draw pictures of this quadratic relation that the generators satisfy, and it looks like the Skein relation. Oops, sorry. I shouldn't start to write and talk at the same time. Okay, so this is a pretty classical interpretation of the Skein relations. So it's pretty well known. And I think this interpretation, I guess, maybe is due to Reshetik and Triumph. I'm not exactly sure. Anyway, it's been known for a long time. So it's another way of thinking of this is that it's a linear relation satisfied by the R matrix for UQGLN. So these braid generators of the braid group correspond to R matrices. So you could also write this as R minus R inverse is Q minus Q inverse times the identity. Okay. Right. So the next thing I wanted to talk about was Hall algebras. So Hall algebras are also related to quantum groups, and I'll explain how in a second. So the Hall algebra is an invariant of an abelian category over a finite field. So if this category is finitary, so that means Hom spaces and X1s are all finite dimensional, then we can define this Hall algebra, and it has a very explicit definition. We'll define these numbers. So these C, M, and E's, these are going to be structure constants for the algebra, the Hall algebra. So M and N are objects in the category A, and so is E. And this number is the number of sub-objects of E, such that the sub-object is isomorphic to M, and the quotient is isomorphic to N. So it's counting the number of ways that E appears in it as an extension of M by N. Okay. Since HOMs in the category are finite, there's a finite number of sub-objects. Well, okay, anyway, this finitary condition implies that this number is finite. Okay. And so the definition of the Hall algebra, you take linear combinations of isomorphism classes of objects so that you make a vector space where objects are a basis. And the product in this vector space is given by these numbers. So the product of M and N is the sum over all E of this number times E. And there's, let's see, and because of the finiteness for X, this sum is also finite. So you only get finitely many E's in this expression. And it's an exercise that's not too hard, but entertaining, that this gives you an associative product. Okay. Right, so one of the first ways that the Hall algebra came up, well, the first way that's relevant for this talk is due to Ringel. And he showed that Hall algebras for varieties, or sorry, for categories of quiver representations give you quantum groups. So I just wrote an example of his theorem here. So this is the type A version of his theorem. He did it for other types also, A to E types. So if you take A to be the category of chains of vector spaces, so these vector spaces are over the finite field FQ. And so the objects of the category are n vector spaces together with a map from VI to VI plus 1. Okay. And morphisms in this category are commuting diagrams of, the obvious thing you would define for commuting diagrams. So this is a type A, I guess AN plus, type A quiver modules. Okay. And so Ringel showed that the quantum group for UQ-SLN is isomorphic to the Hall algebra of this category. And I should be a little careful here. So there's really two parameters. This Q, in the quantum group, Q is a formal parameter. Maybe I should say, maybe for this statement, let me call this parameter V. So maybe I should write the parameter as V. And then I need to specialize V to the prime number or prime power Q. Okay. And how does this isomorphism work? So SLN plus is like the positive part in this triangular decomposition. So it's like a strictly upper triangular matrices. And the way this works is that the Cartan generators E sub I map to, the standard generators E sub I of this quantum group map to the simple object, which is a one-dimensional vector space at position I and 0 everywhere else. Okay. Right. So now I wanted to say a little more. So usually when you work with these quantum groups, you just work with these generators, EIs, FIs, and KIs. But there's a larger set of generators which has some nice relations. So these are the Lustig's PBW basis sort of generators. So these are the analog of the elementary matrix in where there's a 1 in position ij. So Lustig defined these using the braid group action in a subtle way, but they satisfy some nice relations. And in terms of the Hall algebra, they have a nice interpretation. So however they're defined, it turns out that they're equal to the image of in the, let's see. Well, okay, so they map to a nice thing in the Hall algebra. So in the Hall algebra, you can take the object which has a one-dimensional vector spaces in the range from position I to position j. And you take isomorphisms as the maps between them. And so this is a natural, it's an indecomposable object in this category. And it corresponds to something nice inside of this quantum group. And they satisfy some nice relations. So there's, it's not too hard to prove. And a lot of people have done this computation that if you have, so let's say we have a sequence of 4 strictly increasing numbers, A, B, C, D. Then we can take the commutator of EAC with EBD. And there's a lot of cancellation in this commutator when you compute it, and you get a multiple of EAD times EBC. Okay, so there's a lot of indices there. I'll draw a picture of this in a second. So my claim is that this also is the Humphreys-Skein relation. And I don't know an algebraic explanation of this. So, so this is the second way I'm saying that the Skein relation appears. So the first way I said is pretty well known. It's a relation between an R matrix for a linear relation between the R matrix and its inverse for GLN. Here it's a relation satisfied in the positive part of the quantum group itself. And so I don't know, those are just two algebraic objects. I don't need to go through the Skein theory statement, but I don't know a way to relate these two things purely algebraically. Anyway, let me draw a picture. I haven't said why, right? So why do I think this is the Skein relation? So let me draw a picture, and then I'll, the picture is sort of suggestive, and then I'll talk some more about why maybe it's a little more than suggestive. So if we, let's just assume A, B, C, D are consecutive. It'll just make it easier to draw. So the sequence looks like this. Now, what are these two generators? I want to draw, I need to draw two different modules. So let me be a little suggestive in the way that I draw them. So this is the generator EAC. And now this is the generator EBD. Now, you might complain that I haven't said why I'm drawing these with a crossing here. And that's a reasonable objection. Okay. So this is the, I'm drawing this, so the crossing is opposite here because these are the two terms in the commutator here. And now what are these arcs? So the arcs are just representing, you know, this indecomposable module here. So the arcs, I'm drawing arcs where you start and stop the chain of isomorphisms between one-dimensional vector spaces. So this EAC corresponds to the module that has one-dimensional vector spaces at the vertices of A all the way up to C. Okay, in the same way here. And then in the Hall algebra, this commutator is equal to this constant times the following module. So it's a product of EAD. So this is AD, and then this is BC. Okay, so if you want to, you know, if you're generous and draw the diagrams like this is the Skein relation here. So you have it one crossing, you flip the crossing, and then you have the resolution here.
So these overcrossing and undercrossing correspond to the fact whether the extension is of the first by the second or the second by the first, right? Like whether the first is under the second or this or vice versa.
Yeah, exactly.
Mm-hmm.
Yeah, so for reasons I haven't explained, I'm representing the product in the Hall algebra in the vertical direction in the paper. So when AC is over BD, it means AC should be the submodule and BD should be the quotient, or backwards, I forgot the convention, but the point is that between these two diagrams, you switch it, yeah. And then in this,
is there some, I mean, you maybe hinted at it already, but is there perhaps a nice way to compute it, like, you know, actually with diagrams and say, okay, here's this module AC, here's the module BD, and we're trying to, like, you know, you put two rows, and in between you put another row that would be an extension, and then compute it the other way around, and somehow to see that you can even like pictorial view it as a kind of a resolving a crossing. Is there some computation that can be done like that? I mean, I'm just wondering.
I'm not exactly sure. Yeah, I don't know, like an abstract reason why. I mean, you can do the computation on the Hall algebra side sort of explicitly, but I don't, and there's, you know, by computing some extensions in Hom spaces.
Yeah, right, but yeah.
But I don't know how to match the steps in that computation to diagrammatics.
Yeah, I'm just wondering if you can actually depict these as two rows and another row in the middle, and that's the extension up to some equivalence, which perhaps might somehow be made analogous to what you do with the Skein relation. With
Yeah,
links. I don't know.
That's possible. I haven't really thought about how to.
Yeah, no, I'm just wondering. Yeah, thanks.
I guess one more thing I should point out about this is that. Is
that a trivial extension?
Yeah, these two objects commute in the Hall algebra, so there's no extensions between these two objects. So it doesn't. I haven't indicated which order they come in, just because they commute. There's one more nice relation between these things that maybe I'll just write. I don't actually know how to interpret this relation in Skein theory. In classical Skein theory, it hasn't really shown up. So there's a relation like this. Oops, let's see. So now if we take this quantum commutator, this is, oh, I might forget what exactly it is, but maybe it doesn't matter. So in this picture,
Peter, are you going to relate this to surgery later?
yeah, I was going to talk about Fourier categories a little bit. Yeah. Although I still don't know if it'll give well, yeah, we'll see what happens. So there's another a nice relation like this. I might have the constants wrong, I forgot, but this is sort of like a boundary relation. Well, yeah, this is like a Skein relation, but I don't actually know how to interpret it Skein theoretically. Yeah, maybe that's all that I'll say. Okay, so I wanted to talk about one more example of how Skein relations appear in representation theory, and it's going to relate back to this equation 2. So equation 1 was with R-matrices. Equation 2 is these PBW generators in the quantum group itself. And then there's going to be an equation 3 also involving Hall algebras, but in a different setting. And this equation 3, I'll try to explain as a generalization of this equation 2. Okay, so in the previous part, I was talking about the Hall algebra for quiver modules. Another Hall algebra that's been studied a lot recently, it comes from elliptic curves. And it's called the elliptic Hall algebra. So to define the Hall algebra, we start with an abelian category over a finite field. So, and it needs to have finitary properties. So one way of getting such categories is from quivers. Another is from curves. So if you take a smooth elliptic curve over a finite field, then the category of sheaves over this curve is finitary. Okay, so Bourbon and Schiffman, let me write this here too. Bourbon and Schiffman defined what they called the elliptic Hall algebra. And they defined it by hand. So it has some generators, u sub x, x is in z squared. Oh, the dog is joining the talk. Right, so it has these generators, u sub x, and there's some complicated commutation relations. And I won't write them down, but they're explicit. Okay. And they prove the following really remarkable theorem. So if you take an elliptic curve, you can associate two numbers to it, two complex numbers. So these are eigenvalues of the Frobenius operator. And they proved that if you specialize the elliptic Hall algebra that they defined at these two parameter values, then you get the Hall algebra of the elliptic curve. So technically you get the Drinfeld double. So there's a way of taking two copies of the Hall algebra and sort of gluing them together. Okay. And also, well, you don't get the whole Hall algebra. You only get a certain nice subalgebra of it, but that's okay. So this is the analog of Ringgel's theorem. So Ringel showed that there exists some algebra depending on a formal parameter. And if you specialize that parameter to be a prime power, you get a Hall algebra. And what they did is the same thing, except now there's two parameters, Q and T. So that Q and T here, and if you specialize those two parameters to something, then you get the Hall algebra for the elliptic curve. Okay. For the elliptic curve with those parameter values. So it's like a universal Hall algebra for elliptic curves. And it's really remarkable they're able to come up or find such an explicit description of this algebra, because you're doing complicated computations of extensions of sheaves over elliptic curves, and it's a really difficult theorem that they proved. So it turns out that this elliptic Hall algebra is related to Skein theory. So Morton and I gave an explicit description of the Skein algebra for the torus, and Berman and Schiffman gave an explicit description of this Hall algebra, elliptic Hall algebra. So if you specialize their parameters to be equal, then we show that you get the Skein algebra for the torus. And this is just a brute force proof. Once you describe both algebras explicitly, you can just check that they have the same presentation when you specialize Q equals T. So these really complicated relations, which are actually pretty hard to write, involve constants that simplify a lot in the specialization. And it turns out you can write relations for the Skein algebra sort of between arbitrary generators. In the elliptical algebra, that's too complicated. But anyway, so what does this theorem say? It says that the Skein relation is a commutator relation in this Hall algebra. You do have to be careful about this parameter. So there's maybe an amusing remark. So there's, these Frobenius eigenvalues. There's a theorem that sigma times sigma bar is the square root of Q. And actually, to be precise, really I should set T equals Q inverse. And sorry, let me call that, let me call it a Skein parameter, oops, V. Let me call it S, sorry. Okay, so when you make this specialization, Q equals 1. So Q is the order of the finite field. I don't know if this means anything or not, but it's entertaining. Okay. And so now what are, so earlier when I talked about this, the Skein algebra for the torus, I said that one special case of this commutator relation is exactly the Skein relation. So if you translate this over to the elliptic curve side, so this, I say roughly because this isn't literally true because of this specialization thing, but those two curves that I was looking at correspond to actually an average of skyscraper sheaves. And that's one of the curves, and the other curve is just the structure sheaf. So there's a commutator relation in the Hall algebra between these two elements, and that is essentially the Skein relation. Okay. So I want to use this to sort of motivate. I still haven't quite explained. When I was talking about the Hall algebra for the type A quiver, why do I draw the pictures in this particular way? So the way I drew the pictures was sort of motivating that this is the Humphrey-Skein relation, but I didn't really explain why I drew the pictures that way. So I wanted to use this theorem about the elliptic Hall algebra to motivate why I was drawing those pictures that way. So, right? So this part C is about Fourier categories. I don't have time to say very much, but just very roughly. If I have some symplectic manifold Y, the Fourier category is some category defined using Lagrangians in Y. So the objects in the Fourier category of Y are Lagrangians. And the morphisms roughly are intersection points. So I won't really say anything precise about Fourier categories, so I won't actually try to give a definition. That would be another talk. But the point I want to make, so Hollerschuk and Zaslow showed that the Fourier category of the torus is equivalent to the, the derived category of coherent sheaves over an elliptic curve. So X is an elliptic curve over C. So I want to draw a very cartoon formula. Oops. So this formula is not literally true, but is some motivation. So the Skein algebra of the torus is essentially the same thing as the Hall algebra of coherent sheaves over an elliptic curve. And through this Hollerschuk-Zaslow theorem, this would be isomorphic to the Hall algebra of the Fourier category of the torus. So really all these things, none of these are actually literally true for a long list of technical reasons. But it's morally true. So what do I see on both sides? I see some algebra defined with an input being the torus. But I can change that surface and both algebras are still defined. So you might say, is there a relationship? So let me actually just write a question. So this is an optimistic question, but there's some evidence that Ben Cooper and I found evidence that this question is reasonable. So the question is there a relation between the Skein algebra for a surface and the Hall algebra of the Fourier category? So I'm being a little imprecise here, but that's okay. So what I'd want to say is that there's a map from the Skein algebra to the Hall algebra of the Fourier category.
Did you ask a question about the other side of mirror symmetry between Skein algebra of the surface and the Hall algebra of coherent sheaves over whatever the mirror is of sigma?
Oh, I mean, that would also, the thing is on the mirror side, I don't really know how to interpret these curves. So the curves that you get are singular and kind of complicated.
Okay.
And I'm not comfortable enough with algebraic geometry to really have a nice interpretation of what the Skein algebra on that side, I would say.
And in general, they're not Calabi-Yau. The torus is a special case. You get matrix factorizations when going to the B model from other surfaces.
Yeah, in particular, they're singular, and so coherent sheaves isn't quite the right thing to do. Like you need to do matrix factorizations or something like that.
So this SQ of sigma is actually an algebra, not just the module for a surface.
Yeah.
Because I mean, I understand when you have a product space, but here So you usually also have an algebra, not just a module.
Yeah, sorry, I was using there's a notational shorthand, so to save space.
Oh, I see. Okay,
yeah,
okay.
Yeah,
Okay,
sorry.
that's okay. Yeah, sorry.
Yeah.
All right.
Right. So, so Ben and I showed that, well, some things, but in particular, we showed that the Skein relation holds between certain curves in this Hall algebra. So this doesn't actually construct a map, but it shows that if there were a map, some relations that hold in the source also hold in the target. So in particular, the curves in the Skein algebra, curves on the surface, in the description of the Fourier category, you can see, or someone can prove, that there's a natural way of constructing an object in the Fourier category given a curve in the surface. So you get there is a natural map. Well, that's not true. The relation we would expect would take a curve in the Skein algebra to the object corresponding to that curve in the Fourier category. Or maybe some average of objects, but whatever. So we were able to show that the Skein relation holds between certain curves in this Hall algebra. So that's some evidence that the answer to this question should be yes. Now, in particular, we show that this is true for the disk. So if sigma is the disk, then the Fourier category, so to be a little more precise, you need some marked points on the surface, so on the boundary of the disk. So you put n marked points on the boundary of the disk, take the Fourier category, and then you get the derived category of the AN quiver modules. So when we draw the pictures that we would want to draw based on this optimistic question, the product in the Skein algebra corresponds to the product in the Hall algebra. So that's why I was drawing the product in the Hall algebra with crossings. And so this picture, so 2 was the equation that said the Skein relation shows up in the quiver modules. And that's a special case of this optimistic relationship for the disk. So the Skein algebra of the disk and the Fourier category of the Hall algebra of the Fourier category of the disk. Okay, so I'm out of time, so I'll stop here.